right. Now we're going to look at analyzing the motion of objects in general using graphs. Because fundamentally, what we've been dealing with is describing objects by their rates of change, right? Velocity is the rate that position is changing with time, acceleration is the rate the velocity is changing. And what are rates of change? Rates of change are slopes of graphs. So, a graph is a great way of visualizing these quantities as a function of time. If you're given one function, we can figure out what the others look like. So that is our first graph operation, is anytime you have division, that corresponds to the slope of a graph. Rise divided by run. Now, when talking about this, we've been dealing with the average, where it's the average rate of change. Sometimes we're interested in the instantaneous rate of change, or the speed or acceleration at a given time. So we have two sort of slopes we can deal with. If you want the slope at a point, we do the zoom in technique, where you zoom in, zoom in, zoom in to the curve really close, and you draw a line that approximates the slope at that point. Doing this at several points is helpful to get the general slope behavior. So if you want the instantaneous velocity, you take the slope at a specific point where you just zoom in really, really close. Now, if you want the average velocity between 2 points, you just draw a line that connects the 2 points on the curve. We call that a secant line. So a tangent line touches curve at the point of interest, whereas the secant slope is a line between the 2 points of interest. All right, so here is a common, just basic position function we could see. The position of a runner as a function of time is plotted below. So anytime you have a graph, it's usually good to talk about what different things on the graph represent. So if we read this graph, we get position. I know that that's very basic, but there's a lot of operations we can do, and it's easy to get confused when we graph non-traditional quantities. So this is the most basic graph operation you have, which is read the graph. So if you're asked anything about position itself, it must be like a reading/subtraction question. But another operation we have access to is the slope. And what's the slope of a position graph? Well, the slope is velocity. So if we're asked about velocity or speed, which is the absolute value, that is a slope question. So we first need to describe the motion of the runner on each of the following segments. So we can see this is clearly like a 3-segment operation. So we see that we start with the position going up at a constant rate. Then the position is at a constant value for a little bit. And then the position decreases at a constant rate. So this is the velocity is constant and positive. Here, the velocity is constant and 0. And here, the velocity is constant and negative. Right? Because velocity is the slope of position. So I have a constant positive slope. So the runner is going away from their starting position at constant speed. Then the runner stays at their farthest position at a constant speed of 0. So this would be like them resting, and then they go back to their starting location at a constant speed. So this would, if you're making a story out of this would be the runner sprints for 100 seconds, then they get tired and just take a break, and then they jog home at a lower speed. So that's what I have here. Runner moves in the positive direction at constant speed. Then the runner is stopped at their position of 200 meters. Then they return to their original position. So something like that. So now let's calculate the speed. So the speed is the absolute value of velocity, which is the absolute value of the slope, which is just rise over run. So If we look at our 3 segments here, we can just take our little average velocity here. So for our first 100 seconds, we can make ourselves a nice little slope triangle where after 100 seconds, they go 200 meters. So they go 200 meters in 100 seconds. So their speed would be 2 meters per second. Then, really easy to do here, going on at the middle segment, right? Because they are not moving, right? What's the rise? The rise is 0. This is not rising anywhere. So it's 0 over 100, technically, but velocity would be 0. Do I want 0 or do I want to write the word? I will write delta x equals 0. So v equals 0. And now 300 to 400. So 300 to 400. It's the speed on this interval. And I specifically zoomed it in here to show that it doesn't really matter if it's constant velocity, kind of what's happening here. I think I wanted to make you subtract. So let's look at our rise. So technically it's not a rise, it's a fall, right? So this would be negative 100 meters. And 300 to 400, well, that's a difference of 100 seconds. So their average velocity would be negative 100 meters over 100 seconds, which would be negative 1 meters per second. And that's okay, right? That's their velocity. Negative signs in physics, if it's a vector, just represents direction. But we didn't want that. We actually wanted the speed. So we can just say their speed is 1 second. And notice this makes sense qualitatively, right? If we look at our graph, the first segment is definitely steeper than the last segment. So it makes sense that our slope was larger for segment 1. So now let's sketch a graph of their velocity as a function of time. So notice that since it's linear, this is a constant velocity on the whole segment. So everywhere from 0 to 100, their velocity is constantly at 2. Then they stop, right? They take a breather from 100 to 200, so they don't move at all. And then from 200 to 400, they go back to their original position at that lower speed. So it is a negative velocity because they're going back towards their house or wherever they started from for that time. And notice some things here. Also, moving backwards doesn't mean they're actually like running backwards, right? It just means they're going towards their starting position. So notice that we can tell that they sort of didn't displace any net distance because they traveled 2 meters per second in the positive direction for 100 seconds. And then they traveled at half the speed back home, but for double the time. And we'll talk about this next, actually, that we notice actually these areas are the same, which shows that the runner didn't actually displace any net distance. All right, now we're on to a non-constant velocity case, where a car generates the following position time graph. And we are going to draw tangent lines first, whose slopes represent the velocity at 0, 2, and 4 seconds. So what is a tangent line? Well, a tangent line is something that should model the slope at a location. So at 0, it definitely looks pretty flat to me. Then at 1, this would be a good representation of the curve's slope. It only wanted 2, whatever. I'll just show the trend. So this is sort of our tangent line. I didn't draw them very large to avoid clutter, but we can see that it's asking, does the car speed up, slow down, or move at constant speed? Well, speed would be the steepness of the tangent line. So we see that this would be 0 slope. This would be a small positive slope. This would be a larger positive slope. And this would be an even larger positive slope. So we see that our slopes are starting at 0 and getting steeper positive, steeper positive, steeper positive. So our speed is increasing. Since the tangent lines get steeper with time, the speed of the car is increasing. So it is also possible for this to be negative. Like this is also speeding up if your position time graph looks like this, right? Because even though the slopes are negative, they would be getting more negative. So think about absolute value. All right, graph reading time. Oh boy, here we go. Can I read the graph? I hope so. Let's see. What are these counting by? Twos? Yes. Okay. So we start at 0, then 2 meters, then 8 meters, it looks like. 2, then 8, and then looks like 18, 32, and 50. We love Graph Reading Simulator. All right, now we're going to estimate the velocity of the car by calculating the average velocity at relevant time intervals. So we've done this before. We've been saying that, like, if you take the average velocity between 2 times, you're probably going to get a decent estimate for the velocity in the middle. So notice that our times don't match the table times, right? We're given 0.5, 1.5, 2.5. So what that tells us is that what would be a good guess for the speed at 0.5 seconds? Well, we should probably take the average between these 2 times. What's a good average, or what's a good estimate at 1.5? Probably the average on this interval, and so on. So we keep just sliding our slope down a bit. So I think we'll write out to the side sort of what's happening here. So we're just essentially taking the rise over run on each of these sort of adjacent data points. So at 0.5 seconds, well, this would be 2 minus 0 over 1 minus 0, which would give us a velocity of 2 meters per second, right? And then similarly, we would, from the next second, we end at 8, we start at 2, and that would give us 6, and so on. 18 minus 8 is 10 divided by 1. 32 minus 18 is, oh boy. Nope, can't do it. This is my 14. All right, good. That's when I call it quits. I can't do 32 minus 18. And then 50 minus 32 is 8. So technically, I am dividing each of those differences. I'm just doing one, right? Because it's 1 second intervals. All right, describe how our average velocities can be visualized using the graph of x of t. So we're asking, like, how can we visualize these average velocities? Well, essentially what we were doing is we said the speed at 0.5 seconds is roughly the slope of this line. The speed at 1.5 is roughly the slope of this line. The speed at 2.5 is roughly the slope at this line. The speed at 4 is roughly the slope at this line. So we have a special name for that, right? That is our secant line. So we can visualize our average, and we see it is going up, as the slope of the secant line connecting the adjacent data points on the curve. And those do become steeper with time, as we saw from the graph, and as we can definitely see from the numbers. All right, using our approximated velocities, sketch graphs of v of t and a of t. So this is just using our best estimate. We don't know for sure what these graphs look like, but we're going to see a pretty clear trend here. All right, so what we know for sure is what we chose our estimates for the velocity to be. So we see that I did give us that we started from rest. So there's no velocity at 0. And then we're estimating at every half. So at 0.5, we estimated the velocity to be 2. At 0.5, we estimated the velocity to be 6. Then we estimated the velocity to be 10, then 14, then 18. So we do actually see something interesting here. So notice it looks very linear, right? This is 6 points that just make a line. Yes, I did. So let's see. That looks very linear to me, so I am going to actually connect it with a line. So now we have to graph this. So we do know that the acceleration is going to be flat, right? Because acceleration is the slope of velocity. So it is going to be constant. So what is the acceleration? Well, we're asking every second, how much speed are we gaining? Well, we're essentially taking the slope of the slopes. So we could see that the slope between any two adjacent points here is going to be, for example, this would be 1 second for the run and 4 meters per second for the rise. So 4 meters per second per second. And we can check that with any of these data points, right? Our time goes up by 1, our speed goes up by 4. Our time goes up by 1, our speed goes up by 4. Our time goes up by 1, our speed goes up by 4. And that's more clear if we do like this would be like a plus 1 second, and this would be a plus 4 meters per second. And that's constant throughout. So our acceleration is just constantly 4 meters per second squared. So are our graphs consistent with our tangent lines? Hopefully the answer is yes. If you do things correctly, the answer to the is it consistent question will almost certainly be yes. So let's see. We said that the tangent lines look like this. So what does that mean? That means that the slope of the curve gets steeper and steeper and steeper. And the slope of the curve, if its position, is velocity. So our velocity should be going up and up and up and up. If our velocity goes up and up and up and up, our acceleration must be positive. So yes, it is consistent. Because we said the slope gets steeper, which means the velocity increases, which means the acceleration is positive, as expected. And that is that, just in my more formal words. All right, so now we have a tricky part where we are going to talk about sketching these curves from each other in a qualitative manner. So we know that one way we can do it is if we have position, we can just keep taking slopes. So just draw your tangent lines at relevant points and determine, is this a large positive slope? Is it small positive? Is it large negative? Is it small negative? Or is it 0? So anytime you have 0 slope, that would be like your flat portion of the curve, that would mean the velocity is 0 there if it's position. So that will be helpful for us. And if you're asked for acceleration from position, you just do it twice. And this is some wording that we'll use a lot in this class. It's called concavity, where if the slopes trend positive, we call it concave up. And if the slopes trend negative, we call it concave down. Some people like to use like a holding water analogy. Like, would this curve be a good part of a bucket? Like a concave up curve, if I mirrored it, this can hold water without spilling. So that's one way of visualizing what concave up means. But for example, if I do the inverse of that, this would be called concave down, because if I tried to pour water down here, it would spill off the sides. So that's a way to visualize concavity just by looking at it. But it's always easiest to just do the slope twice when doing acceleration curves. Now, if you're working backwards, This would mean you're given the slopes and have to make the original. So just draw a curve satisfying that property. Where if you have a positive value, that would mean you're doing a steep positive slope at that spot. Negative means negative slope at that spot, and so on. But it is important that there's just infinitely many solutions if you're given the slope curve first, because it could start anywhere. So we have to tell you where to start it. All right, so now we're just going to work on some curve sketching. So this is challenging, especially when there's no numbers. So I'll show you generally my methods for this. So if you're asked to go forward, meaning position to velocity, velocity to acceleration, you are just looking at slope trends. So just take your tangent lines and look at what's happening. So for example, we have positive, less positive, less positive, less positive, and they're definitely just flattening out. So that means we're just plotting the slopes. Positive, less positive, less positive, less positive. So it's doing this sort of decay. Then we do it again because velocity, slope of that is acceleration. Negative, 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 but they're definitely going towards zero. So large negative, right? Because steepness represents how far away you are on either axis. Smaller negative, smaller negative, smaller negative. So something like this. Again, we have no way of telling where the values are on the axes. Just try to get the shapes right. Now we'll see these all the time, these wavy ones. If you have a calculus background, you can definitely cheat using your knowledge of what parent function might be. But I encourage you to do it using a purely slope analysis. So anytime your slope is zero, those are good sort of anchor points. So I see that it's zero at each of these spots roughly. I notice it's positive in this connector region. So it's initially positive. Then it's negative in the next connector region. And then it's positive in the final connector. So it looks like we get something like this. Now we do it again. Slope looks like it's zero here. By symmetry, it's probably also zero here. So it looks like it's zero on the ends and right in the middle. Then it's negative in this connector region and positive in the other. So it looks like we get something like this. I think I'll hold off before I explain that property. There's something interesting that happens with the x and a functions that allows me to know I did this right. All right, now let's do it again. It's flat here, here, and here. Not equally spaced. Yeah, that's going to be closer. It is positive in the first connector and negative in the other. That's not that. Looks like that. Then 0, 0, 0, 0, positive, negative, positive. All right. Yeah, there's actually a cool property of these wavy type functions where the acceleration looks like an upside down version of the position. So this is kind of exposing my bad drawing skills, but you see that the hills and valleys line with where they should. Looks like the A is a reflected image of the X. So I'm probably good. I mean, if you're seeing it, it's probably good. If it's not right, I probably caught it and it refilmed it. All right, now we're working backwards, where we're given a slope and have to work backwards, at least partially. So here, this is our velocity function. So if we're just looking at the slope of that for acceleration, acceleration is asking, what is the slope of v? Well, that's just a flat negative, right? Because it's the same slope everywhere in this curve. So that's just straightforward. Now we got to deal with our plot. So The slopes don't tell me anything about where to start. I have to be given that information because anywhere is valid that there. So here it says we start at x equals 0. And our instructions tell us we have a big positive slope, then a smaller positive slope, then zero slope, then a negative slope, and a more negative slope. So it says we should start steep, then flatten out, then get steeper, but the other way. So we get this sort of parabola. And notice it works if we check our tangent lines, right? Steeper, positive, less steep, flat, shallow, steep. All right, now we got to do a double where we have to work backwards twice. So it says assume v0 is 0 and x0 is less than 0. So we're given our starting points. So here we have a constant positive slope. So the tangent line should be the same everywhere. It should be the same steepness everywhere. Well, that's just a straight line. So the velocity function is a straight line with positive slope. And that tells us that our slope should be 0, positive, bigger positive. 0, positive, bigger positive. So I should start flat, and then I should get steeper and steeper and steeper. We can check that works, right? Flat, steeper, and steeper. All right, now we're doing the double, where we got the V in the middle. So let's just do our slope sketch of these for the millionth time. Flat on the ends and in the middle. Negative on this connector, positive on the other connector. All right. And then it says assume we start at 0. All right, now we look at our instructions here. So we have, it says first we go positive slope, then flatten out. So this segment says positive slope, then we flatten out. Then it says we go negative before flattening out. And then we go positive again. And this follows kind of the rule that we said it should, because it's a wavy function and it looks like a and x are upside down versions of each other. So yeah, some tricky curve sketches in there. We'll build this skill as we go on. Yeah, kind of tricky. So now that we've done kind of everything we can with slope, we're going to move on to the other operation. Now, this is one you're probably not familiar with. So every algebra student has been calculating slope since they've been in middle school. But there's actually a third operation we can do. So we said one operation is just read the graph. Next one is to perform division, which is sloping a graph. But also, we could rearrange our formulas in terms of multiplication. So we could say that the distance or the displacement you go on a small interval is roughly v times t. And multiplication can be interpreted as an area. So if you learn math, anything with multiplication using boxes, you're familiar with this idea. So actually what we can do is we can take the area under a graph to get the accumulation. So if you're given a rate, the area under that graph gives you how much that rate has changed the function. And this is a new type of area because it is signed, because rates can cause things to go up or go down. So what that means is that if this is your velocity function, you're moving in the positive direction on this interval, so this area would get a positive sign, and you're moving in the negative direction in this interval, so that area would get a negative sign. But if you want the total distance traveled, you would take the areas unsigned, right? Because we can sometimes care about the total distance, which is just how far did your step counter measure, versus the displacement, which is how far are you away from the starting point, which is when you would deal with the sign. And the difference between AP1 and APC is AP1 will stick to these nice geometric shapes. Physics C, you get to do functions and take some calculus operations there. But you will see that all my graphs are going to be nice geometric shapes and not circles. All right, so here's a velocity function for a car. So we're going to take inventory here where we have 3 operations. We have read, we have slope, and new to the party, we have area. So we have a velocity graph. So if I read a velocity graph, it is, of course, velocity. We have the slope of a velocity graph. So what is the rate of change of velocity? Well, that is acceleration. And then we have the area under the graph. So the area would be, what is velocity the rate of? Well, it's the rate of your position changing, also known as displacement, which is also distance traveled in this case because there's no negative parts. All right, so what is happening to this car? Describe the motion. Well, this is speed. So the car starts at rest, the car gets faster and faster and faster, and then the car maintains that speed. The car speeds up and travels at constant speed. All right, let's calculate the car's acceleration at t equals 5 seconds. What is acceleration? Well, acceleration is defined as the rate of velocity change. So this is the slope. So we just need to make ourselves a little slope triangle at t equals 5 seconds. Now it's weird because it wanted not the average, but the instantaneous. Well, that's okay. It's a straight line, right? If I draw a tangent line here, that is actually just this line slope. So we can just rise over run this. So the velocity goes up by positive 40 in a time interval of 10 seconds. So our acceleration would just be 4 meters per second, also known as a meter per second squared, representing it as that second rate of change. Clear that for when we need to analyze it later. All right, little mini QQT. Begin between 0 and 10, the car travels D1. Between 10 and 20, the car travels D2. So we're basically asking, on what half of the car's motion does the car travel more distance? So we have the 0 to 10 interval, and then we have the 10 to 20 interval. So which one of these is the car moving a greater distance? Now, there's a couple approaches to this. I'll kind of reason through both of them. First reason is, notice that, first of all, the intervals are the same, right? They're the same length. So it's the same time, but notice that on the 10 to 20, the graph is higher at all points. So we can see that the car is actually going to travel further on the 10 to 20 interval because the graph is always taller. Now, if you wanted to argue that distance is the area under the curve, you could argue that the shapes made have the same base and same height, but one is a rectangle and one is a triangle, so we get less area in the triangle. If you wanted to take a geometry argument, right? Because it's 1/2 base height versus base height. So I kind of gave you both here. So D2 is bigger than D1 because the velocity graph is taller at all points. So there's a larger area under the graph. Or you could also say from 0 to 10, the speed increases to that maximum value, but on 10 to 20, that maximum value is maintained the whole time. So on average, your graph is just taller on the second interval, so the distance will be bigger. Let's calculate that distance. So our distance traveled is just going to be the displacement. Technically, the magnitude of the displacement. I usually don't write this, but in this case, it is just going to be the area Now, if you're a geometry pro, you might recognize that this is a trapezoid, and you might know the formula for the trapezoid. Don't use the trapezoid formula if you're not comfortable with it. Just break it up. So we always design shapes that can be broken apart. So D1 is going to be the area of this triangular shape, and D2 is going to be the area of this rectangular shape. You can assume almost every graph in this class will be either a rectangle, a triangle, or a combination of those. So this is D1 is this area, and D2 is this area. It is clear that D2 is definitely big. So this would be the first area plus the second area, and let's work those out. So the area of a triangle is 1/2 times the base, which is 0 to 10, so that's 10 seconds long, and the height is 40 meters per second. You can check that units will work here because this is 10 meters, 10 seconds, and this is 40 meters per second, so we will get an answer that is in meters. So half of 10, that's 5. Yeah, I don't know why I didn't think that. Half of 10 is 5. And then 5 times 40 is 200 meters. Then for D2, you're just a rectangle. So the area of a rectangle is just base times height. So the base spans from 10 to 20, which is once again 10. And then the height is once again 40. And we get 400 meters. So we get 200 meters plus 400 meters, which is equal to 600 meters. And we do see that the second area was twice as big. So it agrees with our claim. All right, let's sketch a graph of the acceleration and the position. All right. Well, we said on the first interval from 0 to 10, this is a constant, acceleration is the slope. So the slope is a constant value of 4 meters per second, actually, we found earlier. And then on the second interval, the graph is flat, so there's a slope of 0. So for the first 10 seconds, the slope is a constant value of 4 meters per second squared, and then it is 0 for the second 10 seconds. Then the position of the car, assuming we start at 0. All right, this one's a bit tricky. So we do know that these represent our slopes of position. So speeding up from 0 to 10 means my slope should get steeper and steeper and steeper and steeper. So it should definitely arc upwards on the first 10 seconds. And then on the second 10 seconds, the velocity is constant, right? The slope is 0, so the velocity is not changing. Velocity is not 0, so it is not this, because the velocity is not constantly 0, so it's not this. So it's actually straight line, right? Constant velocity means straight line. So it actually just maintains that sort of slope. So I might make this kind of exaggerated just to show you the curves. And then it stays constant. It should be, like, the slope should be continuous at 10. It's bad. So I might show that this is a pole. So this is concave up, and this is linear. I'm writing it so you know that my drawing is terrible. It's hard to show this subtlety that it curves up to start, and then it becomes linear. So anything that's like this kind of works, where it's constant on this interval and it curves up. That's kind of tricky. All right, now we have a case where we're going to account for sine. So the vertical velocity of a tennis ball as a function of time is plotted below. Define an upwards velocity as positive. This means the ball moves up at 30 meters per second, then it moves up slower and slower and slower until it stops. Then it moves down faster and faster and faster. All right. So when is the tennis ball slowing down versus stopped versus speeding up? So there's some shortcuts here for what does slowing down mean versus speeding up from a velocity graph. Slowing down means that you approach the x-axis, technically the t-axis. And speeding up means you move away from x-axis. There's also a sign rule where if velocity and acceleration have the same sign, that means speed up. Because velocity points, acceleration points in the way velocity is already pointing in, so they add like this. Versus opposite directions, V and A, the vectors would try to cancel. But I like this idea where if you're getting closer to the axis, it means slowing down. If you're getting farther from the axis, it means speeding up. So, or just look at the numbers, right? If the numbers are getting bigger in absolute value, you speed up. If they're getting smaller, you slow down. Slowing down, notice the numbers on the graph are getting smaller on 0 to 3. Uh, the graph is exactly 0, stopped at t equals 3. And the numbers are getting bigger in absolute value on 3 to 6. So we see that the ball slows down, then the ball stops, then the ball speeds up. Calculate the acceleration of the tennis ball. So let's do that. Well, acceleration would be the rate that the velocity of the tennis ball is changing. So we have a couple options here. There isn't really a grid, so it's hard to tell for sure what's happening. But we can see here that if we draw ourselves a little slope triangle, the rise would be negative 30 meters per second, and the run would be 3 seconds. Now the scaling looks a bit odd here, but we don't have a grid, so we just have to, we can definitely say that it's 0 right here, and it's 30 right here. That's all we can say for sure. And it's definitely linear. So our slope would be negative 30 meters per second over 3 seconds, which would be negative 10 meters per second, or negative 10 meters per second squared. How interesting. Why did I say that? Indicate whether the tennis ball is in free fall. Justify using the calculated acceleration. Well, we said upwards is positive, so the acceleration is negative 10 meters per second squared down, which is exactly equal to g. So we are in. So we are definitely in free fall. So we should say yes, right? Anytime it's an indicate, we should say yes or no. So since acceleration is g, we are in free fall. All right, what's the vertical displacement on 0 to 3? What's the vertical displacement on 3 to 6? What's the total vertical distance on 0 to 6? Okay, so it is important that displacement is signed. So that matters here. So our first interval is from 1 to 0 to 3 seconds. We see that this is a triangle. So our area would be 1/2 times 30 times 3. So this would be our displacement. It is positive. And then we have from 3 to 6 this. And this would be negative, because it's under the axis, 1/2 times 30 times 3. How do I know that it's 30 still? Well, one, we see it's a constant slope. So if 3 is right in the middle there, we know it's going to reach negative 30. Also, you could just do free fall counting from that idea, right? After 1 second of falling, because it's stopped right here, after 1 second of falling, it would be negative 10, then negative 20, negative 30. So notice that these cancel, which should make sense, right? If you throw a ball up and the ball hits the ground, you have displaced 0 distance. It makes sense that these areas will be equal and opposite. So let's calculate those. So the vertical displacement on 0 to 3, this would be like our first area, which would be positive 1/2 times base times height, which would be positive 45 meters. And then we'll do one of my favorite answer techniques when I don't feel like writing a whole lot, is I will say this is negative 45 meters by symmetry. You write by symmetry, it automatically just sounds like you know what you're doing. We proved it, of course, right? This is pretty symmetric. And then what is the total vertical distance traveled by the tennis ball? So we do know that delta y net is equal to 45 minus 45, which is equal to 0, but that's not what we want. That is not the total vertical distance. That's the vertical displacement. What we want is the distance, which is just the absolute value of the areas. So it's not 45 minus 45, it's 45 plus 45, which is 90 meters. Exactly double one of them. So that's a pretty standard canceling question. So let's make some position graphs and acceleration graphs now. So the acceleration, well, that's pretty easy. It's free fall. So anytime you're in free fall, you get this. It says do a numerical scale. This is just negative 10 meters per second squared. And then the vertical position y of the ball, assuming y of 0, 0. So what did we figure out here? Well, first of all, we figured out that by the canceling idea, there's no net displacement. So after 6 seconds, the ball should be back to where it starts. But then also, we found that the displacement on any of those half intervals was 45 meters. So when the ball's traveling up, it travels up 45 meters. And then when the ball travels down, it travels down 45 meters. So this point right here is actually 45 meters, right in that middle point here. We'll try our best to be symmetric. I think I can do better than that. Maybe. I don't like that. We can do better. Good enough. Good enough for government work. So that is our full description of this little free fall thing. So notice that's kind of why we drew our dot diagrams in the previous section like that, right? Because the position time graph of a free fall object will make that upside down parabola. And notice we get the symmetry from the parabola as well. All right, last thing, we could be given the acceleration graph. And this is just like a double where you have to work backwards twice. So just like vt is a delta x, at is a delta v. So the area under an acceleration graph is the velocity displacement, or just delta v. It's how much the velocity changes by, with sign, of course. So to summarize, this is just a good table to not, commit it to memory, but this follows just from the definitions of everything. If I read position, I get position. If I read the slope of it, I get velocity. The area under the position graph doesn't tell us anything. The units would be meter seconds, which doesn't make sense. So just look at the units. Read velocity, I get velocity. Slope velocity, I get acceleration. And if I area velocity, I get change in position, also known as displacement, delta x. If I read acceleration, I get acceleration. If I slope acceleration, I would get the rate that acceleration changes, so meters per second squared per second, in this class, we'll usually assume that acceleration is constant. So it's kind of meaningless that the slope at that point. There's technically a name for it. Like it's a pretty well-known thing that it's actually called jerk. So the slope is actually jerk. Although in most of our cases, we're dealing with zero jerk scenarios. So even if it made sense, we just are not defining this. And then the area would be the change in velocity. So we'll just do a acceleration graph analysis and then get out of here. All right, the vertical acceleration of an elevator as a function of time is shown. The elevator is initially at rest at y equals 0 at its starting time. So let's describe the motion of this. So the elevator is initially just sort of like stopped on the ground. At this time, and we're just asking what's happening. So on our first interval, we see this is clearly split up into 3 chunks. On our first interval, we see that the elevator will be constantly accelerating up. So it starts with the velocity 0, and I just keep adding up arrow, up arrow, up arrow, up arrow to the velocity. So the elevator speeds up at a constant rate in the positive y direction. So the elevator is traveling up and speeding up. Then my acceleration is 0, meaning there is no change to the velocity. So it speeds up, speeds up, speeds up, and then it's at that constant fast speed for a while. It was at constant speed. And then on that last interval, I give a constant negative acceleration. My velocity's up. And whenever directions disagree, that means you get a slowdown, right? Because if I have an up vector that needs to change in the down direction, they're going to fight each other and cancel. So we get a slowdown. So that's our motion here. Let's calculate the velocity change of the elevator at each of the given intervals. So we should say, now that we have this, we know that since this is acceleration, if we read acceleration, we get acceleration. If we slope acceleration, we get nothing. I'm not writing the x because it looks like position. And then if I do the area, I get delta v. So that's what I want. So I want the area in each of these cases. So area from 0 to 4. This is just a 4x1 rectangle. Then I have a 0x4 rectangle. And then I have a negative 2x2. So what are our changes here? This would be 4 meters per second per second. Sorry, 1 meter per second times 4 seconds, which gives positive 4. I can't do math. Positive 4 meters per second. Then I have 0 meters per second of change. And then I have negative 2 times 2, which is negative 4. So our elevator speeds up by 4 meters per second. Then it maintains that speed. Then it loses those 4 meters per second and actually stops. So quantitatively accurate graph of the velocity of the elevator. Well, we know on the first 4-second interval, we must gain 4 meters per second. We do start at rest. Then we gain nothing from 4 to 8. And then we lose it all by the time we're back to 10. So we get a segmented trapezoid that's not unlike what we got from our position graph from the runner. Let's calculate the total distance traveled by the elevator. Well, how do I get distance? Well, I can't get it from acceleration because there's the velocity middleman function. So I do know that the distance would just be the displacement in this case. Should really call it delta y. And that's just going to be the total area under the velocity graph. So this is just going to be 3 areas added together. And luckily, we just made a velocity graph. So this would be 1/2 times base is 4 times height is also 4. And we have base is 4, height is also 4, no 1/2. Then we have base is 1/2, base is 2, height is 4. So, see, that gets us 3 areas that we have to add together. All positive, because the elevator never moved down at all. Might have slowed down, but it was still moving up. So we get half of 4 is 2. 2 and 4 makes 8. Then we get 16. And then we get 4. That gets us 8 and 16 is 24. 28. And we got to do the position of the elevator now. So this one's going to be funky. And it's all qualitative here. So we know that on the first 4 seconds, we speed up. So we get that nice upwards arcing concave up. Then it's linear for 4 more seconds. Trying to make this linear. This is 5. So we have concave up, we have linear, and then it slows down to a stop. So we actually know it has to flatten out at 10 from this slope, which means it's got to do something like this. Took me a couple tries to get it flattened out. This is CC down. Wow, that's quite tricky. Always got to end with a weird looking one here. All right, that is basically everything we could ask about motion graphs. So again, the key here is think about this table. Write your verbs for every graph. What does it mean to read the graph? What does it mean to slope the graph? What does it mean to area the graph? It's not likely that all 3 mean something, but usually at least 2 of them do. So it is really important because how you analyze something is much different if it's an acceleration graph versus a position graph or velocity. So think about that.